We're recording. Okay, great. So again, we're talking about section 5.1, simplifying trig expressions. You guys know about simplifying. You guys done simplifying many times with quadratic expressions or other stuff. We're doing kind of something similar here. Reciprocal trig identities. Did you guys cover this? Cosecant, secant, cotan. Does that seem familiar? Yeah, really simple. Cosecant is 1 over sine. Secant is 1 over cosine. Cotan is 1 over tan. Why cosecant doesn't go to cosine? I don't know. I'm not sure. Why secant goes to cosine? I don't know, but we just go with it. Pythagorean trig identities are right here. Quotient identities we talked about. Even odd identities, cofunction identities. You know, actually, we do have an opportunity where I could talk about the Pythagorean trig identities. I'll actually do this right on my screen. So let's kind of backtrack a little bit. Let's go back to the unit circle. Now, the unit circle. What's the center of the unit circle? What's the radius? 1, perfect. That's why it's called the unit circle. It has it's a very basic circle, right? Center at 0, 0, radius of 1, right? Now, you guys might remember that there's always different points on the unit circle. And they're all spaced up by various degrees, right? Like, for example, this is like 0 degrees, right? That was 90 degrees. Remember, we go counterclockwise, right? The positive direction is counterclockwise. Both this all bring stuff back, right? And then you had a bunch of angles in the middle. Like, for example, you have 30 degrees, 45 degrees, and 60 degrees, right? Not the best diagram. I could do a little better. But now, do you guys remember, like if I ask you, for example, the coordinates at 30 degrees are √3 over 2, comma 1/2. And say I asked you to find me the sine at 30 degrees. What would be the sine at 30 degrees? You guys remember? How would you use this to find the sine at 30 degrees? Which one? What is it? The y value. Yes, exactly. It's the y value. So the sine at 30 degrees is 1/2. How would the cosine at 30 degrees? What would I say for that? That'd be the x coordinate. Exactly. So very important. The x coordinate is cosine of your angle. And did you guys use a symbol theta? Yeah, theta is just, it's the Greek alphabet. Don't play Connections, by the way, from the New York Times. No, I think the one 2 days ago was on Greek letters. I should know. I actually totally missed it, but a lot of math uses Greek letters. I don't know why. We just do. Oh, sorry. What am I? I'm losing my mind here. Sorry, that's sine theta. I should know this. Sorry about that. Okay, so x is cosine, y is sine. Y over x is tangent. Y over x is tangent. Well, why is that? Well, think about it, right? If theta is right here, and that's 1, and that's x, and that's y, self-cotone, right? So means what? Opposite of hypotenuse. Y over 1. There you go. Cosine, comma, right? Adjacent hypotenuse, x over 1. There you go. Comma, over a, y over x, tangent. There you go. So not that hard. Well, if you think about it, what's Pythagorean theorem, guys? From back in the day, middle school, a squared plus b squared equals c squared, right? You know this. A squared plus b squared equals c squared. Well, x squared plus y squared equals 1, right? By the way, you guys did conics. I know you guys did conics. We did it actually in the fall, sorry, the spring of last year. But you guys did conics also. What's the equation of the circle here? X squared plus y squared equals 1. Why? Because where's my center? 0, 0. What's my radius? 1. So that makes sense. X squared plus y squared 1 from a circle standpoint, or conics, that totally makes sense. Also, I just replaced a with x, b with y, and c with 1. Now, what is x again on the unit circle? Cosine. What's y again in the unit circle? Sine. Boom. Substitute it. What do you get? Sine squared plus cosine squared equals 1. That's where it comes from. You're simply looking at the unit circle, realizing that that's cosine, that's sine, and that's 1. That's where it comes from. It's very, very simple. To get these other two variations, personally, if I don't teach precalculus or trig for a while, I actually forget the other two variations. But I do know that I could divide both sides by, say, sine or cosine. What if I divide both sides by cosine? 1 over cosine is going to be secant. Sine over cosine is tangent. Cosine over cosine is 1. So if I actually were to divide each of these terms by cosine squared, I would get that third line. What if I divided each of those by sine squared? I would get the second line. If I divided these by sine squared theta, guess what? Sine over sine is 1. Cosine over sine is cotan. 1 over sine is cosecant. Okay. And do you mind putting the phone away? You don't need it right now. Thanks. Yeah, no problem. So you could derive these other two. Another thing you need to be mindful about too is this right here. If you see this, that means sine times sine. Just be really, very careful. It's not sine. See, if you do this, that's confusing. But that means you're going to square the theta first. And then do the sine. So this right here can also be thought of like this. We don't write that because, just to be honest, math is just so lazy. I'm incredibly lazy with this stuff. So we want to do things shorthand notation. So we see this square next to the sine means sine theta and squared. Just yeah, or sine times sine. The other ones we'll talk about when the time's right. Like why is that true? Why is that true? Why the cofunction identity is true? When the time comes, we'll talk about it. So now let's get down to the nitty-gritty. Let's do some of these examples here. And yeah, we got about 3 pages, but this should go by pretty fast. This will go by pretty quickly. All right, so let's start with example 1. I think what I'll do, I'll kind of walk you through one of the examples, then pause and kind of have you guys try the second one and share what's happening. This is really like a puzzle, to be honest with you. It's really like, hey, here are all the different puzzle pieces, right? All the formulas. I just gotta apply it to this example. So you're asked to simplify, right? Okay. One rule of thumb. One rule of thumb. Any expression not sine or cosine, make it sine or cosine. Make it sine or cosine. That's just going to make the simplification much easier. That's really kind of the golden rule here. Anything that's not sine or cosine, make it sine or cosine. So now, this is your best friend. Or that other formula should I give that's color coded, right? Well, that's not really color coded, just color. Let's look at secant and let's look at tan. According to the first page of this notes or the formula sheet that I gave you, might want to have the formula sheet right next to you, so you don't have to keep flipping back and forth. What is secant? What can we substitute for secant? 1 over what? Sorry. 1 over, yeah. Well, not so. You're correct in terms of, so when you say 1 over x, you're talking about cosine, right? So let's write 1 over cosine instead. Yeah. Now I know what you mean when you say that. That's more for evaluating. We're not evaluating. Yeah. That's something else. Now tangent. What is tangent in terms of sine or cosine? According to your formula sheet, it should be right there. Sine over cosine. Good. And then lastly, you have cosine x. Okay, so once we've done that, now the fun begins. Actually, I'm gonna get the formula sheet here too myself. Okay, now the fun begins. Start crossing stuff out, right? What can I cross off? The cosines. Wait, did you mean, hold on, let's back up a little bit. Did you mean these x's? They can't, oh, don't want to do that. Okay, let's back up a little bit. Why is that bad? I'm glad you guys said that's that question. It's PEMDAS, guys. It's PEMDAS. What about root x plus 1 over the cube root of x plus 1? Can I cross off those x plus 1s? No. Because guess what? Cross those x plus 1 is division. A radical is like an exponent. That's like x plus 1 raised to 1/2. That's like x plus 1 raised to 1/3. I can't cross out those x plus 1s because guess what? I got to take care of this before I do this. Like if I were to plug like a number like 1 in, for example, I get √2 or the cube √2. That's some like nasty number. But if you just say, oh, I'll just cross them off and the answer is just 1, no, that's not true. You can't do that. It's the same thing with this here. You can't do that. Like if you have sine or cosine, you got to do, there's actually a parenthesis, believe it or not. I know I didn't drop the parentheses. There actually is a parenthesis there. You'd have to take care of that and take care of the sine before you even divide. So please don't cross those off. But I can cross these off because those are two of the same function. That I can do. That's totally fine. So I'm glad I asked that question. All right, so let's cross these off here. So we're stuck with after I cross this off. Sine x or cos x, right? No, because you only have one. Because there's two of these here. There's only one of this. If I had another cosine x, go for it. But you gotta do one at a time. So I'm now stuck with that. Now look back at your formula sheet. What's sine or cosine according to your formula sheet? And done. Is that more simplified than original? Totally. And that's the whole point. We want to make this look simpler. Why we're doing this? Trust me, when you do move on to calculus, because I've taught calculus also, you're going to have to be able to simplify expressions so you can apply calculus principles to them, because it's going to be really hard to do some calculus stuff if you have a very nasty expression, you don't know how to simplify it. So this is part of your toolkit as you move on to calculus next year. I know you don't quite see the big picture. Trust me, you'll see the great forest, great vista when you get there. Okay, let's try example 2. So I'm probably going to do some more substitution, right? Actually, before I do that, let's back up a little bit. Another rule of thumb. Factor, if you can. Why not? So you have this minus this. Whatever's a minus or plus in between expressions, factoring will be a possibility. So look for it. Is there something common between both these expressions? Pull it out. Totally. Pull it out. So you pull out cotangent x, and you got this. That might make things a little easier for us if we do that. I think it's still been okay if you didn't. It just means you're doing a little more substitution, but I think it might make things easier. Now, according to our formula sheet, what can we substitute for cotangent in terms of sine and cosine? Well, we could do 1 over tangent, but I probably do cosine over sine, yeah. Because what's going to happen is that if you convert everything to the same thing, it's going to make canceling much easier. Sometimes it might be better to say 1 over tangent, but in this case, I think let's just make it cosine over sine. And secant 1 over cosine, we know this, right? And I'm going to make this cosine x over 1, by the way. Cosine x over 1. You'll see why in just a sec. That's why I love Zoom, because I can code very easily. If I combine these two fractions, these denominators are not the same. How do you combine fractions by addition and subtraction? What happens if you trade off both denominators? They're not the same. That's cosine, that's 1. What I do is make them the same. By what? Cosine x, yes. So you got multiply top and bottom by cosine x. So now it becomes cosine squared x over cosine x. Does that make sense what I just did? Yeah, we're okay so far. Okay. I need a little more space, so I'm going to do this. I'm going to delete this because now you guys know it's up. I'm going to move this up. Oh, hold on. Move this up top. All right, here we go. So now go back to black. Cos x over sine x times, and now I can combine those two fractions. Okay. We're okay so far? I just did combine these two. And it wasn't terribly obvious when it was 1 cos x minus cos x. But by making it a fraction, anything can be a fraction. You can see one. Just put it over 1, right? Anything divided by 1 is a cell. Make it a fraction. And then you realize, oh yeah, multiply top and bottom by cosine x. I can combine the two fractions. Okay. Now they're combined. Do you guys see the next step? You have this times this. Is there something common between the numerator of the first and denominator of the second? What can I cross off? Cancel. Cancel cosine. Love it. Perfect. Yes. Let's do it. So now you got 1 minus cosine squared x over sine x. It's there. I told you I'm a big football fan. We're now in the red zone, right? We're about to punch this in. We're going to hand out to Christian McCaffrey. Just kidding. No, I love football. But yeah, we're ready. We're ready to score here. 1 minus cosine squared x is not terribly obvious. I'm going to tell you right now what it is. And hopefully you guys can see why I'm doing this. And final answer is going to be this, by the way. But let me explain what I just did in green. Okay. So I know we're clear on this part. We know the possible code. We know that. So we have this. 1 minus cosine squared x is sine squared x. So it's not terribly obvious, but let me explain why. Remember we had this earlier? Yeah, I told you like in my mid-40s and all my friends they faced some release, right? And I just showed you now why it works with that here. What if we got the sine squared by itself? What do you have on the other side? But right? We're going to be measuring today. And guess what? We have 1 minus cosine squared x. So what did I do with this? I replaced this with what? Exactly. And why would I want to do that? Because I see sine at the bottom of that function. And what does sine squared x mean? Sine squared x means sine x times sine x. We just talked about this. So what can I cross off here? A sine x from both top and bottom. Leave me with what? Just a sine x. That's why that works. It's kind of like saying this. What if you have a squared over a? How would you reduce it? What would that reduce to? A squared over a. What does that become? Hey, this is why we covered exponents in algebra 2. Remember we did all the algebra, all the exponent rules? It's for these moments. Now you got to be comfortable with exponent properties, right? That's exactly what I'm doing. I'm doing an exponent property, really. Because you have two signs up top and a sign down below, and the two signs up top are being multiplied, so I can cross them off. So all that, believe it or not, becomes sine x. There's a little bit of work though, but in order to get there, you have to substitute, and you have to. There's a rule of thumb: try to replace anything that's not sine or cosine to sine or cosine, make your life easier. Questions? We're cool. We're good so far. Okay. And again, if you ever need to watch this, you have the video now. I think it's better to actually watch than just look at the fill notes. Because the fill notes may not make any sense to you. When you hear the annotations, it makes more sense. So if you ever need to rewatch, now you can. All right, let's move on to these two. I'm going to give you guys a little bit of a push here and kind of walk around and help you guys out. If you get stuck, it's okay. Help you guys out. I would actually FOIL here. And here. Let me close the door because it's a little distracting. I'm going to use a formula sheet for this part right here. So it'll be negative sine theta times negative cotangent theta. I'll let you guys kind of keep going with that. Here I'm going to FOIL this. So that's going to be sine x plus tan x. It's going to be a little messy. Sine, oh, geez.
Then you do this one, mark it on here, put your name on it. You guys stop talking. Class. When you do your wingspan, mark it and label it on here.
Please, thank you. All right. Anyway, you're gonna have to foil that. And please, 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 tell them to be calm and you know, very much. I'd be very friendly about stuff. But the one thing I really don't like. Please, please, never ever do this. Please don't do that ever. Okay. So remember, you have to foil. You can't just square the sign. You can't just separate. Some students will do this. They'll say, "Oh, that's sine x, sine squared x plus tan squared x," and call it a day. No, it's not distributed. You can't do that. That's one of the things that actually really bugs me. So don't do that, please. Make sure you got to foil. You have no choice. You have to foil. So yeah, so you foil. Unless you have another sine x plus tan x in the bottom, I suppose. So go ahead and do that. I'll walk around, help you guys out. I'm actually going to freeze the screen and work out the answers, then we'll share. Talk to each other, help each other out. Actually, the first one, the example 2 should come out very nicely if you do it correctly.
Okay, wait, sine times tan. You can do cancel out as sine and sine. Because you look, what is like sine, well, tan, the tan is a sine. Okay, so first we have a sine. We have a sine square. Sine square cosine.
This is almost.
No. So, oh, you have another cosine.
Okay. Anyone make some progress or questions so far? How are we doing?
Yeah, not that. So you're like when you're foiling, right? So sine times sine is sine squared.
Yes.
Like tan times sine.
Just sine times tan. Yeah, sine times tan.
Can that be simplified into cosine?
No, because tan is sine over cosine, unfortunately. It could be, you can still put a sine square over cosine if you wanted to, but I wouldn't do that way. Because it's gonna, the whole business.
Yeah.
So when you foil, so guys, let me walk through what I just did. So sine times sine is sine squared x, tan times tan is tan squared x, and then you have the outside and insides. Sine x times tan x is sine x tan x, and you have another one, sine x times tan x. That's why you got two of them. And of course, you have cosine squared x and you have negative secant squared x. Does that make sense? How I did? Hold on. Let's color code again. So what's circled in light blue is the same in the bottom step right below, right? Sine times sine squared x, tan times tan squared x. That's sine tan, another sine tan, you get two.
So should we leave it in like tan and all of that?
Yeah, I'm kind of, yes, I'm kind of going against what I was preaching. I think that's not sine cosine, mainly because, and it will make more sense when we talk about our next page, which is called verifying trig identity. Because sometimes what you want to do is like, you'll have like this mass expression on the other side will be an equal sign, and you'll see like the tangent's gone. The hope is that the tangent's cancel. So, and how do you know that? You don't, but trust me, when we look at the other problems, it'll be a little more clear why you'd want to keep that standard. And of course, these other two stay the same. I didn't touch these two. I just kept them the same. They carry it up. So what's happening in light blue? You guys see that now? The FOIL. You guys get the foiling part, right? First outside, inside, last. First sine, outside sine tan, inside sine tan, last tan. Now this is the part. This is really the key step. Like, and by the way, as a test question, the third step actually, what's the points would be? It's a really key step. What was sine squared plus cosine squared again? We thought it was 1, right? Sine squared plus cosine squared. This one, that's why I have it in green. This is not so obvious. But remember I said one of the other variations, secant squared x plus 1. Is that correct? No, I lied. Tangent squared x plus 1 equals secant squared x. So if I were to move the secant squared x to the left side, and the 1 to the right side, tan squared minus secant squared is -1. So what's happening in orange here, tan squared minus secant squared x is actually -1. So what's happening in green is +1. What's happening in orange is -1. Well, what's 1 minus 1? 0. After these go away, what are you stuck with? 2 sin x or a tan x. What happens to the tan x here? You cancel, what are you stuck with? That's why I think that's the answer. Trust me, we'll have more chance to practice this. It's a little intense. I know it's a bit heat up of a problem. Which, yeah, go ahead. Yes.
This is every time here says.
So you have 2 of them, right? That's like,
Yeah.
right. You got.
And then every time.
Oh, so 1 minus 1 goes away, right? So now you have all multiplication on top. 2 times sine x times tan x or tan x. Because these are all combined by multiplication, right? After the 1s go away, you cross out the tans. It's kind of if you have this. What if you have 2xy over y? What happens to the y's here? Totally, because multiplication.
Also, it's 2 times x.
Exactly, yes. Because what's the opposite of multiplication? Division.
Yeah.
You can do that. What you can't do, please never do this. You can't do that. That you can't do.
So if I write this out, it'll be like. Would it be like this?
No, you're not swearing. Remember, there's a plus and sign.
On there.
That's why I combined the two. Not yet. It's like combining like terms.
So then it's 2 over, so then it'll be just 2 sine x.
Or another thing you could do too. No. Because 2. Now you're distributing twice. Now that comes 4. It's not distributed because it's not plus sign. Right? It's just 2 times, like for example, if I have 2 times 4 plus 3. I mean, sure, I can distribute the 2 to both, right? But if it's 2 times 4 times 3, it's just 2 times 4 times 3. That's all it is. Yeah. Now, another thing you could have done too, you can factor tan x. From up here, that one. Once you got these going away, you can factor tan x. Or this one, you can factor tan x. Then hence, and sin x plus sin x, which is still 2 sin x. That's the other number, but I think it's easier to keep it all lumped together. Yeah. All right, example 4, guys. That was an easier one. That's just cosine theta. Remember, your formula sheet tells you sine negative theta is negative sine theta. Cosine is negative cosine theta. That's what your formula sheet says. The 2 negatives cancel. In this case, I would convert cotan to cosine over sine. The sines cancel, and you just get cosine theta for example 4. Example 4 is not quite as intense. Example 3 was definitely intense. Don't worry, we're gonna see more of these. We're gonna see more of these down the road. One thing I want to mention about these guys here. Think about unit circle, right? So you got 30 degrees. What's the sine of 30 degrees? It's just the y coordinate, which is 1/2. Now, what if I went the other direction? Negative 30 degrees. The coordinates there are √3/2 still, and negative 1/2. So what's the sine of negative 30 degrees, guys? What's the y coordinate negative 30 degrees? That's why we see sine negative theta. It's just negative counterparts. Likewise, a tangent and cotangent. Cosine won't be that way. Cosine theta, cosine theta equals cosine negative theta. Those are the same thing because regardless of whether you go clockwise or counterclockwise, you're gonna get the same thing. Because it's looking at the x coordinate. All right, let's move on to 2 more examples, and then we'll verify identities, and then we're done. Okay. So I'm going to kind of go through this a little more quickly. So this right here, I know is negative sine theta. Just use your formula sheet. This right here is negative tan theta. Use your formula sheet. Now, coming back to, actually, where'd my formula sheet go? Cosine of pi over 2 minus theta. That's going to be sine theta. And this one here is going to be cosine theta, correct? And let me just get a highlighter here. It's going to get a little bit colorful. And let's switch colors again. Okay. Colors here. All this makes sense. Sine negative theta, that's just my formula sheet, negative sine theta. Cosine pi over 2 minus theta is sine theta. Sine pi over 2 minus theta is cosine theta. Tan negative theta is negative tan theta. By the way, pi over 2, that's radians, right? What's pi over 2 converted to degrees? 90. Do you guys know why we call cosine cosine? Where the co comes from, the CO part? You know what the CO is short for? I'm not sure that would make clear to you guys because there's a lot of transition when things are going down. The cosine is for complements. Do you guys remember complementary angles from geometry? What did that mean when you had complementary angles?
Together, they equal 5.
Yeah, 90, exactly. Cosine is a complement of sine. Pi over 2 is 90 degrees. So if you do the complement of cosine, it's going to be sine and vice versa. I'll give you a quick short little example so you can make sense of it. What I'm going to totally make up some random values here. Let's say this is like, I'm totally making this up. I don't know if this is actually stuff. Totally making this up. So what if I did a sine of 35 degrees? What's that going to be? 3/4, right? What if I did the cosine of 55 degrees? What's that going to be? Cosine of 55. Adjacent over hypotenuse. So 3/4. They're the same. These add to 90. It's not a coincidence. When these two angles add to 90, and you're doing a sine and cosine, those values will be the same. So sine of 35 degrees equals cosine of 55 degrees. Or, if I call this theta, that'd be 90 degrees minus theta. Or 90 equal pi over 2. That's why that works, just so you know. There's a rhyme or reason. It's not some random crap that's, oh, just do it. I want to make sure you guys understand. And again, it's still sinking in. You'll probably forget after today. Don't worry, we're spending all month on this. It'll sink in after a while. Okay, now I've done this. Let's clean it up. The top becomes what? Negative sine theta. Sorry, negative sine squared theta. My bad. And the bottom becomes, I'm going to convert the tangent to cosine over sine. Sorry, sine over cosine. And that's where the fun begins. Okay. What happens to the, so you got two things to consider. You have all this here, and you have all this here. And you have this giant fraction bar, right, that connects, that separates the two. What happens to the cosines on the bottom? Cancel out. So you're stuck with negative sine squared theta over negative sine theta. What happens to negatives? Cancel out. And yet now you got sine squared theta, which is really just sine theta times sine theta, right? Over sine theta. What happens to the sine thetas here? More canceling. What are you stuck with? Boom, got it. I'm actually going to show you guys. How do you know you've done this correctly? Because you're probably thinking to yourself, okay, I'm doing all this stuff. I think I'm doing, I just don't know if I have the correct answer. I just don't know, right? There are a couple cool ways you could verify your work. I'll show you on Desmos first, because that's a little easier. And I'll show you in the graphic calculator how you can do it. So if I go to Desmos, so I could actually y equals sine x. Right? There you go. There's a graph. You guys should know that. Or y equals parentheses. And what was it again? It was what was it again? It was sine, goodness. Sine negative x times cosine 0.5 pi minus x divided by sine 0.5, just type pi for pi, minus x times tan negative x. Okay, it was a lot of typing, I agree. But guess what? I don't see two graphs, do I? So you know you've done it right, because the others open. If I turn this one off or do that, they're the same. That's how you know you've done it right. If you graph, you can do the same thing in the graphing calculator. Graph calculator is a little harder to punch in, but you can do the same exact thing. Or you can also do this in the graphic calculator. Really quickly, let me show you. I think it's all recorded, so you can just watch this again if you need to. Math department. Because obviously you can't use Desmos on a test. The SAT, by the way, for those who are juniors, if you do the digital SAT, they do have Desmos built into the new SAT, which is lovely. Yeah, it's all on computers. Yep, it's world's changing, dude. All right, but you could have done was this. If I type in that wacky equation, what was that wacky equation again? With it's gonna be a pain to type, but sine negative x times cosine 0.5 pi minus x. Okay, make sure I put double. I told you it's not okay. Good. I did double parentheses. I'm okay so far. Divided by sine of 0.5 pi, or should have pi over 2, minus x times tangent negative x. And make sure I'm in radian mode, which I am. Okay, now, you guys may not know this. If you hit alpha and trace, you can call up anything you stored under y1 to y0, anything. So it's like a function. And just type in a random, so you're plugging a number into that function. Great. Now let me do sine of 1, because that was my final answer, right? Sine. Got the same thing. That's how you know you've done it right. That will give you confidence on a test or a quiz. Did I do this correctly? If you get different answers, you may have punched it wrong in the calculator. That's possible too. But if you punch everything correctly in the calculator and you get different answers, you know your work is incorrect. You got to go back and double check it. That's how you know. And if you get it right, congratulations. Move on and pat yourself in the back. You got it. So that's something that I'll encourage you guys to do often to make sure you know you got it. Because it's scary. Like you don't know if you got this right or wrong. It's so nasty. It came down to sine theta. No, you could. What do you mean you use it for? I don't know. Yeah, I'm pretty sure we'll allow graph because the reason why graphic calculus may have been disallowed for previous tests is because if you're asked to do like sine like 330 degrees, you just punch in the calculator, right? Or graph something in the calculator. Now at this point, yeah, I think graphic calculus should be allowed for this. Yeah, I'll find out. Let's look at example 6 really quickly here. Okay, and you guys have been very, very patient. I appreciate you guys. So let's see here. I would do this. So you have to be really adept with your factoring. Do you see what do you see what I just did? Yeah, I did something called the difference of two squares. So all that factoring stuff you did in middle school and algebra 1, if you are a senior, you probably had algebra 1 here, right? Probably had it during the Zoom school. Am I correct in assuming that? Yeah, the seniors, you guys started here when we were in Zoom school. Yeah, you guys remember we were out in the tent. Crazy time. Crazy times. It's actually 4 years ago that we started talking about COVID. Like this thing called COVID that's gonna hit us. Crazy, right? Where we come. Anyway, there was two squares. That's just this. You guys might remember that. So that's exactly what I did here. I did the difference of two squares. And I could do it again. I'll do it again. Secant x minus tan x. Secant x plus tan x. And then secant squared plus tan squared x. Is there, I don't think that's an identity. Yeah, unfortunately, I can't do anything about that. So I just leave it like that. Actually, let me backtrack a little bit here. Let me backtrack, guys. I kind of messed up. That's final answer. Okay. Why did I mess up? Because remember what I said? Tan squared x plus 1 equals secant squared x. If I were to move the tan squared x from left to right, guess what? Secant squared minus tan squared is 1. That's all 1. I should realize that. Because after all, I'm trying to simplify, right? Not trying to make it worse. So the answer is secant squared plus tan squared x. And there's no identity for that last part. Okay, given that it's almost 12:30 and you guys still have another class today, I'm thinking I'm going to hit the pause button. We'll finish off these notes because it's actually kind of a nice little segue to what we'll do on Friday. So the homework pack I'm going to hand out, you're not going to do all 12 problems for homework 30. It's called, I don't know why it's called homework 30, but you're not going to do all of those problems. You're only actually going to do 1 through 8. And yeah. So we can pass it. Now this homework packet is for all the homeworks, the whole unit. And let me stop the recording.